Okay, for setting up the simulation demos, there's not really that much to do other than rerun the simulations. As far as the nonlinear one goes, we mainly show that at the start because it is very visual. But the one thing to keep in mind is the refine results is both for the lid and the intermediate component being pushed down. So it's a little bit more visual if you wanted to show something after the fact. But for live demonstrations, just run the first study. And as you probably know, that when you're dealing with simulations, it's the path to the results. So if you move them around, you're just going to make sure that you update the pathing. So you go to your properties and make sure that path points exactly to where your files are. But for size reasons, we can't include all the results in the deployed demos. So the main order is the critical ones to show are the nonlinear live results, the load case manager, and then the shell manager. The other two are optional. So with the load case manager, we have two key studies set up. The first one is to just show how to create the load cases, and the second one is already run. So just make sure that you've already run the results for the fin study. It doesn't really matter whether they match or not. You can see here we've got multiple loads set up, and then just when we go to load case, simple thing to do is you just want to add the torque load option, and they've set it up now so that you only have to unsuppress the loads of interest, and it will actually update up here once you do an update. So to add a load case combination, you can either take the default, which doesn't make sense really, but I just usually pick from, for example, maybe I want the 20G vertical plus 2 times the torque load, or load case 5 in this case, but again, name them appropriately. That's the main thing to show. Also to mention the sensors, that you can add sensors here very easily. And then obviously when we go to load case manager with the results already run, you can look at the results view. And one of the other things you might want to mention, I don't think it's really good for this particular model, is you can transpose the data if you need to look at it in a different format. So have your load studies across the top here. Problem is for me is that obviously in this condition you really want the results at the top, not the conditions. So anyway, just something to keep in mind. Then optionally, if you want, you can talk about the dynamic enhancements with the frequency response curves. So this bracket is undergoing obviously a lateral base excitation by default, and that's why we get our mode shape. Now if you look at the current mode shape, sorry, it's put that behind it. There we go. You can see the peak is around 430 or 443, and then there's not much else happening in this case, so it's pretty single excitation. But the main thing is to use the frequency response graph, show the different effects. So mode number doesn't really show that much, so that's why I don't mention it. It's just shows you the variations with frequency and mode. Whereas the effective mass participation is the best one to show the contributions in each direction, and then obviously you can come back and show the cumulative effect, which basically it keeps increasing the components. So you can see for the first mode, the Z component has a big jump initially and then smaller jumps, whereas the others have large jumps later on based on their contributions. And then obviously the concept of supporting dynamic fatigue loads now from either harmonic or random vibration, and you can either mention that you can come in and pick a particular frequency, or you can do multiple blocks to look at damage accumulation from repeated cycles at different frequencies. That's up to you. Obviously this doesn't take very long to run, so it's pretty quick and easy to show the data. Then the third one to show is the Shell Manager, which is again designed for managing lots of surfaces. And then I've got the two sets of results here to show for the edge bonding. It's taking a while. There we go. Different ways you can get to the Shell Manager, obviously from the Command Manager, or you can right click on the main branch or on any of the bodies to get to the Shell Manager. So the dialog here is for creation, which we don't really need to do because it's already set up. One thing to note is if we go to the bottom, you'll see these are the sheet metal components. So you see the thicknesses there, but you cannot change the offsets because it's already inherited from the sheet metal body. You can change material, and I suppose you can put those in a group, but you won't be able to assign the thickness. There's two ways you can assign thickness. You can either do it through the group, so if you go to manage groups and change the thickness there, or you can just punch it in here and it will assign it to all the other components in that group. So pretty convenient. There are some graphics issues still. You can see it's a little funky on my machine at the minute, but it's showing some funky shading on the sheet metal components. But other than that, it's a very useful tool. And then the whole purpose of the 2014-2015 is to show the improvements in automatic bond detection. So we have these sheet metal brackets here which have a 0.1mm gap, and in the past it would not automatically bond those even if you did set a gap tolerance for edge to face bonding. So this is what you would get. Whereas in 2015 we get a much improved result where it's automatically detecting that bonding, and you can show that if you really want to by the definition here. So as I said, the other two demos are a little optional. We have support for cyclic symmetry and nonlinear. The main thing here is to show the cyclic symmetry results and the definition, so you can see it like that. And I've got one set up before and after, so here's one set up just to show it on the cyclic component, and then obviously with the show it on symmetry option. And just when you animate it, the best trick I find is, if you want to make it look good, is just do the bounce, because it just makes the animation better. It's the same thing for the next one. So when we go to the self-contact, and probably the refine one is just a little bit more high res, takes a little bit longer to solve. I'm not sure if I got, yes, about an hour and a half. But the main thing again is to animate the bounce and then to show the self-contact. So in terms of, if you only pick one face now, you get self-contact. Turn off your symbols and again do the bounce. So the first animation isn't as good, it's just capturing it, but then after that it's quite nice. So really there's not too many challenges with this. There are a couple other things you can talk about. There's the ability to control running multiple studies. So you can see you got run specified studies, which is quite nice. And also we have a new option for the Intel based direct sparse, but I don't have any performance data on that yet to show the performance gain in having a Intel dedicated solver. But we'll try and get that to you as soon as we can.